Okay, so it's my pleasure to introduce Serge Cantat from University of Rennes, the program area, and he will talk about topological entropy and algebraic transformation.
Okay, so I want to talk about topological entropy. And what I call dynamical degrees. Okay, so I mean both are non-negative real numbers. Topological entropy is a number that when associated to a dynamical system, which is defined by the iteration of a continuous map of compact metric space. And dynamical degrees are associated to algebraic transformations of algebraic varieties. So roughly speaking, the dynamical degree of a transformation G, which is algebraic, is the following. You write G as an algebraic transformation, so you write explicit algebraic formulas. So you just look at the degree of the formula, but then you do that for all iterates of the transformation. So you get a sequence of degrees. And the dynamical degree is a number which captures, which measures the exponential growth rate of this sequence of degrees.
The measurizers, is that what you said?
I will define it precisely. Okay. And the relationship between the two numbers is the following. If you have an algebraic transformation of an algebraic variety which is defined about the complex numbers, then the topological entropy will be the logarithm of the dynamical degree will be an upper bound for the topological entropy. Okay. So I want to discuss this topic, and what I want to do, I want to show that these numbers are, or maybe in certain special cases, interesting numbers. So I will do that for topological entropy in dimension 1. So I will describe something which is due to surface. And then for dynamical degree, I will describe a joint work with Jeremy Brook. Yes. Okay, so I will, in fact, give two talks, one for topological entropy and one for dynamical degrees. Okay, so let's start with topological entropy. Okay, and the definition, so you start with a compact metric space. And then consider a transformation F from X to X, which is continuous. Okay. And then you look at the dynamics, which is given by the iteration of X. And you want to count the number of orbits that you see when you observe the dynamics. So you fix epsilon, a real number. And you say that 2 points X and Y have the same orbit between time 0 and n at scale epsilon if the distance between X and Y is less than epsilon. And this distance remains smaller than epsilon when you iterate the map for all first n iterations. Okay. That's less than epsilon for all. Okay. Okay. So now X and Y, the orbit of X and the orbit of Y can be distinguished. So are distinguishable if for some iteration between 0 and n minus 1, the distance is more than epsilon. So now you count the number of orbits. Number of orbits. Scale epsilon during time n. First max of the set S, of the cardinal S, the whole set S, where S is the subset of X, so that for all X and Y and S. distinguish or x given by n is different can be distinguished from the other. At scale. Okay, so it's a finite number. And typically, this number grows exponentially fast when you let the time of the period of observation goes to infinity. So you take the exponential growth rate, log the number of orbits divided by n, and you take the soup when n goes to infinity, and then you let the precision epsilon be better and better, so the scale goes to 0. And that's what we call the topological entropy. So the topological entropy does not depend, I mean, if you change a distance into an equivalent distance, then you get the same number because of the log. And if you take an isometry f, then of course, if x and y, if the distance is less than epsilon at time 0, then when you iterate, since f is an isometry, you do not separate the points, so the entropy of an isometry is 0. More generally, the entropy of f is bounded from above by the dimension of the manifold times the logarithm of the Lipschitz constant of f, if f is a Lipschitz transformation of a finite dimensional compact manifold. And if you take a torus of dimension n, and take the multiplication by some integer k, so f of 1 x n is just kx1, kxn modulo integers, then you get an equality here, so that the entropy of f is n times the logarithm. Okay, so what I want to do now, I want to describe a result of Kerston for entropy of continuous transformations of the interval. So x now will be just a unit interval. So I is 0, 1. Look at the dynamics of transformation of the interval into itself. So first an example. We'll take so here is the interval. 1. And now you take a transformation of the interval which is a piecewise linear map with constant slope. When I say constant slope, I mean that the slope is constant in absolute value. Okay, so the slope is lambda. Okay, so the slope is constant. Okay, and the map is surjective like this one. Then what you get is the entropy of f. Absolute value of the slope. Then you get logged on. Okay, so the value of the entropy can be any it's log plus of lambda, so the sum of lambda. So what you get is the following simple fact that every non-negative real number is the entropy of a continuous transformation of the interval. Okay. So the values of the entropy are not so interesting if you do this remark. But now I will focus on a particular type of transformation, and we explain that the value, if I make nice restriction on f, the values of entropy are very nice. Okay, before I do that, let me introduce a few notations. So, let's say a turning point for f, so f is a continuous transformation of the interval, is a local maximum or minimum for the graph. Okay, so it's a point where the graph looks like that, or so it's a notion of critical point, but I mean this kind of critical point is not a turning point. And now the modality of f the m of f is just the number of turning points. And the total variation of f so it's just the length of the curve f when you think of f as a path in the interval, the parameterized by 0. So it's the integral of the absolute value. So it's the length of the path given by f, where f is a path in 0. Okay, so here is our first result. Which is due to Univ. Say the following, so if f is a continuous transformation of the interval, f has finitely many turning points, so the modality is finite, then in fact we can count the number, you can compute the topological entropy as a limit. It's the limit of the number of turning points. And it's also limit of n log of the total variation. So the entropy is, you can say here that the entropy is the following. You compute the length of the graph of the nth iterate, and you measure the exponential growth rate of this. So now I can describe Kerston's theorem. And for that we shall make an assumption on the dynamics of f. So here is the assumption, and say that f is post-critically finite if you take the turning points of f and you take the orbit of the turning points, and these orbits are finite orbits. Okay, so you have a finite number of turning points, of critical points, where the graph, the monotonicity changes. You have a finite number of points like that, and the orbit of each of these points is finite. And then the statement is the following. the entropies of F for all continuous transformations of the interval, which are prospectively finite. So you get the set of numbers. And then you have the second set of numbers. You have the set of numbers alpha, which are real numbers, such that alpha is an algebraic integer. And alpha is larger than or equal to the absolute value in the modulus of all its conjugates. So for all beta Galois conjugates. Then the theorem is that the two sets are equal. Okay, so maybe I should explain a little bit this hypothesis here. So alpha is the number that I consider. So alpha is an algebraic integer. So it's an algebraic number, but more precisely, there exists a polynomial p with integral coefficients of p of p. It's a unitary polynomial, such that p of alpha is a root of p. And you can choose p with a minimal degree, so you can take p a minimal polynomial for alpha. And then the Galois conjugates are the roots of. Okay, so for example, if you take the golden mean, then it's a quadratic integer, and there is exactly one conjugate, which has modulus less than 1. So it's the golden mean. So I want to describe not the proof, but one step is easy direction. So the easiest direction is the fact that this, I made a mistake here. There are rods everywhere, so that's okay, so I want to explain one direction, so I want to say a few words why the exponential of the topological entropy is such a number. Okay, so this is related to the previous results by Kerston, which I like to call the striking theorem. So it's the following. You start with a transformation of the interval with finitely many golden points. And then what the theorem says is that you can replace, if you want to compute the entropy of F, or study the dynamics of F, you can replace F by a piecewise linear map with constant slope. So there exists, statement is like that, there exists a projection pi from the interval to the interval. So it's C0 and it's onto, it's subjective, such that, and there exists a map G from the interval to interval, which is piecewise linear continuous and with constant slope. So the derivative, the natural value is constant, equal to some number lambda, for each real number t in the interval, which is not a point where the monotonicity changes. Okay, such that, first, the dynamics of F projects on the dynamics of G under the projection phi, so phi equals to F is G equal to phi. And second, the entropy of F is the same as the entropy of G. And this is log lambda. Okay, so you can replace F by a simpler map, which is just linear, piecewise linear, and maybe you lose part of the dynamics, but you don't lose much since you keep the same entropy. And moreover, if F is post-critically finite, then you can choose G as to be post-critically finite. G is post-critically finite if F is post-critically finite. So let me sketch the proof of that under this assumption, assuming that F is post-critically finite.
So the idea that the entropy is related to lambda is that points close together can be spread on the factor of lambda.
Yes, yes.
So they're growing.
Yes, exactly that. Okay, so let me explain how one can try to construct G, assuming that F is post-critically finite. So I assume, and doing that, I will try to explain why we get this kind of number. So assume F is continuous and post-critically finite, and also assume for simplicity that these are subject. Okay, so the interval, so that's the diagonal, and the graph of it. So I have a finite number of turning points, but also I can take the orbit of this point and I get a finite number of post-critical points. So I take the orbit of this point, the orbit of this point, and I get a finite number of points. So maybe points here. So now I cut the interval I, so I is here, into these smaller intervals that I see. So E1 is here, I1 is here, and I is here. Okay, now I'm looking for G, which should have the same combinatorial behavior. With constant slope. So here, this interval will correspond to a decomposition of I in intervals J1, J2, up to Jr. And the combinatorics of the transformation here should be, I should be able to read the same combinatorics on the right. Now, what is the dynamics of F on this picture? If I take a small interval, Ij, and I apply F, there is no critical point for f on this interval, because the points that I used to cut the interval I are exactly the critical, the turning points for f, and it's iterate. Okay? So when I apply that, what I get is a consecutive union, a monotonic union of intervals here. Okay, so it's a union.
If you compose a map, you have a lot of factors in the derivative. The zero can be anywhere to make a zero. So this is forward. The critical point's back here now.
Yeah, but what I said is correct.
I'm not following it. I'm not following it.
Yes, but I just apply f.
Huh?
I'm just mapping it by f. I'm not iterating. F is just the sign.
You're doing one iterate?
Yeah, I just do one iterate.
Ah, okay.
So this point is not supposed critical.
So here I have critical points, and then what I say, I cut the interval along with a post-critical orbit, okay, which is fine. Then I cut and I get a sequence of smaller intervals. And now I apply that just once. Okay. And this is a union of intervals. Okay. So I can, so let's say, okay. So I don't want to use notation, let's say 1, 2. Okay. And so now you can construct a matrix which is the incidence matrix for this relation. Okay. So you put a number, you put an integer if the image of the at place ij, if f of ij contains ij. Okay. This is that matrix. Then here you should have the same incidence matrix, but the map G has constant slope lambda. Okay. So the length of these intervals correspond to an eigenvector for this matrix. Okay, because the length of G of the length of G of Gi, so the length of that is just lambda times the length of the interval. And at the same time, the image of the interval is a union of intervals given by these combinatories. So the matrix is a matrix with non-negative entries. The coefficients are non-negative. And the length of the intervals should be an eigenvector or the eigenvalue. Lambda is the slope. Okay, so the map that I am looking for, so the map G, at least I know the slope. Because I know the matrix here. And now it's a matrix with positive coefficients. So I can apply Theorem theorem. If you have a matrix with positive entries, then there is an eigenvector with positive coordinates which correspond to an eigenvalue, and this eigenvalue is in fact the spectral radius of the matrix. Okay, so there exists an eigenvector. For the eigenvalue, which is the spectral radius of F and F, so that's max of the absolute value and of the moduli of identities, such that the entries and the coordinates are positive. Okay, so this is just Theorem for for this matrix. So this is given by F. So now I get two things. I get what lambda should be. Lambda should be this spectral radius, and the length of the intervals G1 up to GL should be this length. Okay? So this eigenvector is well defined up to a multiplication by a positive number. Of course, I have a constraint here that the sum of the lengths is equal to 1. I just scale. So this does not provide a complete construction of G, but at least it says what lambda should be and what the length should be. Okay? And now, see, so the entropy of G must be log lambda. So it's a log of this spectral radius. It's the max of these eigenvalues. Okay, but then it's an eigenvalue of this matrix which has integral coefficients. So it's an algebraic integer. And also part of Perron-Frobenius theorem says that, sort of part, it's written here, all other eigenvalues are smaller than or equal to this maximum. Okay, so I get this. So this, the fact that this set is contained in this one is not very far. But what Bill Serge proved a few years ago is the opposite conclusion. Okay? So that's the end of my first talk. Okay, so if you are lost, you didn't understand. And now is the second story. Okay, so now I change the topic. I think it's far.
You went over 3 minutes.
Yes, that's true. It's precisely. Now I want to talk and to describe a few things concerning birational transformation of the plane.
But those things are not continuous. Are they?
Yes, they are not.
So how can you relate to the previous discussion?
You will see. Okay, so birational.
It's always worrisome.
What?
This contact is not continuous.
Yeah. Okay, let's start with birational transformation. So I just want to consider the case where so you can do what I'm going to do for algebraic varieties over the field. Okay, so here the algebraic variety is just the affine here. Okay. With coordinates. Affine coordinates next one. So rational transformation is just a transformation which is defining affine coordinates by rational fractions. So f of xy is p of xy p of xy all of here where p, q, or s are polynomially two variables, so q over q or over s are rational fractions in k of s. So k is so here it's the affine plane for the field k. Okay?
Okay, now what structure are these the transformations of? I would have thought you'd take two polynomials and overlap the affine space and the affine space.
So this map, the affine space is the affine space.
So what structure are these the transformations of?
Okay, so you can look at the field of functions of the affine space. And the field of function is just this field. Okay? And then, so let me first define birational transformation. Okay. Birational transformation, just rational transformation F, such that F is a rational transformation, such that there is G a rational transformation, with F composed with G composed with F, which is the identity. So it's xy equals to xy. So now birational transformations are automorphisms of this field, which are the identity of the field K.
Equal to that?
Yes, so birational transformations of A2 defined like that correspond to automorphisms of the field K1 fixing the ground. Okay, it's completely trivial, Q.
Okay.
P over Q is the image of X, and R over S is the image of the indeterminate core. Okay, let me give examples of birational transformations. Okay, so the first example, you can take a affine transformation. Okay, so a linear part plus a translation. Yeah. These transformations are well defined as well. The second example is what we call the Rennes transformation, or Rennes map. So, take xy and map it to, for instance, x, epsilon y plus x squared plus c. Okay, so it's invertible because you know x and then you know y. Okay, at least if epsilon is not 0. When epsilon is 0, you see that the x-axis is invariant, and the dynamics is the dynamics of x squared plus c on the x-axis. Okay, so the dynamics of this transformation when you iterate when epsilon is 0 is the dynamics of x squared plus c in one variable. Okay, so if you work over the field of complex number, you get the Poitou-Julia dynamics. And when epsilon is not 0 but very small, it's an invertible deformation of this Julia. So this transformation, at least over the field of complex numbers, there are examples with very nice dynamics. Okay, the second remark is, instead of x squared plus c, I can put p of x here. P, any polynomial transformation. Polynomial in one variable. So this birational transformation, you see that the number of parameters is infinite. I mean, the degree of P is not bounded. So the dimension of this group is infinite. So now I come back to the remark that you did about concerning continuity. So here you can look at monomial transformation. So you take a B, C, D, a matrix with integer coefficients and determinant plus or minus 1. And you consider the transformation xy goes to x to the A, y to the B, x to the C, y to the B. It's invertible because the inverse corresponds to the same transformation but for the inverse of this matrix. Okay, so you get an embedding of this group into the group of birational transformation of the thing. Now look, take this one. That's a y over x. 1. That's an example. And look at what happens when you take the family of lines to the origin. So here you are along the line, y is equal to s times x, where s is the slope of the line. So the image is just s what? So this picture is transformed into this one. Here is the x-axis. And each line is mapped to a vertical line. Where here you read the slope of it. So the map is not continuous, and it's not well defined, and it's not continuous there. You got an indeterminate sequence, 0 divided by 0. And in fact, this point is mapped to this line. So then, if you blow up the point, so if you replace this point by the P1, which corresponds to the projective space of all, projective line of all direction tangent to the origin, then if you blow up the surface, you get a well-defined map from this new surface too. Okay, so when I said that I have transformations of the affine space, the affine plane, I'm cheating a little bit. So there are indeterminacy points. The map are not well defined, are not continuous. Okay, so now what is the dynamical degree? Dynamical degree. So there are two ways to define two equivalent ways to define the notion of degree. So first, a geometric definition. So degree of f. So you have a birational transformation f of the plane, and you want to define the degree. So you take a line in the plane. You take the preimage of the line. Okay, so it's an algebraic curve. And then you intersect with another line. And once you take the intersection, you count the number of intersection points. And that's the degree. Okay, so it's a degree for generic lines L and N. So if you prefer, it's the same as this intersection where now you use interfacial theory and I don't want to describe this dot. Okay, so the second definition is with formulas. And for that it's better to work not in the affine plane, but in the projective plane. So the projective plane is just the affine plane with a line at infinity. Here I have affine coordinates xy. Now I have homogeneous coordinates xyz. So x is just, when z is 1, capital X, capital Y corresponds to xy. Now a birational map of P2 can be written like that in homogeneous coordinates. You can always write f of x, y, z as P2 R. So these are not the same P2 and R as in the previous notations. Now P2 and R are homogeneous polynomials in x, y, z of the same degree. Which I denote by D, and without current factor of positive. Okay, so let me give an example. So of course, the degree of that by definition is this number. Just one example. Take the monomial transformation, which corresponds to the matrix minus identity. Yes, x, y equals to 1 over x. 1 over y, in homogeneous coordinates. It's the same one. So it's 1 over x, 1 over y, 1 over z. Okay, so it's not written in this form. I can multiply everything by the same numbers, okay, because it's homogeneous coordinates, so I multiply everything by x, y, z, so it's y, z, z, x, x, y. And now the degree of degrees. Okay, so geometrically, if you pull back a line, you get a conic. You see, it's an involution. You know that transformation by sigma. It's an involution. So the degree of sigma composed with sigma is 1. Okay, so the identity. So the degree is not multiplicative. In fact, it's submultiplicative.
The point is that it's not actually defined as a map P2 to P2.
Yes.
Based on
Yes.
QR.
So let me say, so the degree of F composed with G is bounded from above by the product of degrees. And in fact, it's equal, except if the following phenomenon appears. There is a curve which is mapped to a point by G, and this point is an indeterminacy point of F. So you always have inequality, and you have strict inequality when this geometric phenomenon occurs. So if you map a curve to a point, this point is mapped, it's an indeterminacy point of F. It's mapped to a curve. Okay. So, but now this inequality says, implies that this number is quantified. So that's the dynamical degree of F. Take the limit when n goes to infinity, degree of F to the n, 1 over n.
So in this particular example, you could actually make this an involution of P2 blown up at 3 points.
Yes,
right? But
yes.
That's not the typical.
An involution is quite boring from a dynamical point of view. So for example, if you take the Rennes map, there is degree of P 2 or more, then this map is not conjugate after any kind of blow-up to a regular. Okay? So there is no regular model for this on a complex projective surface. Okay, so let's continue and use your remark. Okay, so let's look at the dynamics of that acting on P2. Okay, so the degree of f to the n is the degree of f to the n, except if the following phenomenon occurs. So there is a curve C, the curve is mapped to a point, then the point is mapped to another point by f, and so on. And after a finite number of steps, you arrive at an indeterminacy point, f, which is mapped to the inverse map to curve. Okay. So, if you don't see this picture, the sequence of degree is just multiplicative. But if you see this picture, you can just blow up the point in the middle. So you blow up this point, you blow up this one, you blow up this new point. And now, if you do the blow up correctly, the curve is mapped to this new curve, this one to this one, this one to this one. So you kill the phenomenon.
So you will have a sequence of maps.
So now, in the neighborhood of the curve, you have a sequence of maps.
The neighborhood of the...
From here to here, I don't say that, but I will look at what happens here. And when I do that, I reduce the number of indeterminacy points by 1. Okay, so in a finite number of steps, I don't see this phenomenon anymore. So this is due to this remark, and the precise quote is due to bigger than half. And the statement is the following. So there exists, so let F be a biracial transformation. So of the plane, so it's better to work with P2 instead of the affine plane. Then there exists phi, so there is a surface X and a projection from X to P2. So this one is a well-defined morphism, so it's a well-defined algebraic map. So it's a morphism, and X is just obtained by blowing up a finite number of points in P2, and the projection is just blowing down the curve. Okay? And there exists, so such that so F hat is just a conjugate of F on X by phi, so it's so such that you keep this phenomenon. Okay, so now the degree is multiplicative. Except that the notion of degree has changed, and the notion is the following. So you look at the action of F on the. So let's suppose that the field is the field of complex numbers. We use geometric, more geometric words than what algebraic geometers do. So you look at the action on the second homology group of X, and this action is multiplicative. Satisfies Fn star is F star n for all. One way to say that the degree is not multiplicative is to say that the action of the transformation on P2 on the second homology group is not, does not behave well under composition. Okay. The degree of a curve is just the same as the homology class of the curve. So now what you get after a modification of P2 by a finite sequence of blow-up, you get a matrix with integer coefficients, and you get a multiplicative behavior. So if you iterate the map and look at the action on homology, or if you look at the action on homology and iterate, you get the same. Okay. And then on this surface, the dynamical degree is just the spectral radius. So it's not very long.
So the thing that you lost by blowing up is you no longer have just a single generator for H2, so you can't just ask
yes.
what the sales
So
are.
here, yes, let me say what you just. So here, let's do that here. So you start with P2. Then the second homology group is just Z. So it's Z times the class of a line. That's H2 for P2. And then if I take a point, and I blow up the point, then I get a new curve. So as a curve, it's a P1. So let me call it E. Then the second homology group is, has dimension 2, is D times the class of a line. So get a line here, get a line here, plus Z times the class of the curve. And here you have the intersection form on cohomology, or on homology. So if you take two curves, you can count the number of intersections. So here, if you intersect two lines, you get 1 point. Same is true here, two lines, you get 1 point. If you take a line, a generic line, it does not go through the point, so it does not intersect E. So these two classes are orthogonal. And here, the self-intersection of E is minus 1. If you blow up n points, you get Z times the class of the line plus Z 1 plus Z n. And the intersection form, you have 1, the plus sign here and the minus sign. Okay, and it's an orthogonal orthonormal bit.
You must work on there's head on the right, there's no head on the right, right? Or
Yes.
there's
Parts here.
Yeah.
Okay. And so this is an instance of Hodge-index theorem. And the fact that the intersection form is non-degenerate and the signature is plus, minus, minus, minus. And now you use this intersection form and the action of the Biracial transformation on the homology, and you get restriction on the possibility for random. So using this fact that the signature is plus, minus, 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 and the action on homology, you can prove something more. You can prove that lambda out there is, so it can be equal to 1, of course, or it can be a Piso number, or it can be a sign. Okay, so let me recall what Piso and sign are. So you take alpha an algebraic integer. So alpha is a Piso number. So assume from the beginning that alpha is real and positive. Alpha is a Piso number if all conjugate, Galois conjugate beta of alpha, which are different from beta, are in the unit circle. Okay? So the picture is, I will draw the picture of it. So you have 0, you have unit circle, alpha here, and all Galois conjugates around. Here. Okay? That's a Piso number. The silent number is when, so for instance, if you take just an integer like 2, integer 2 is a Piso number. The set of Piso numbers contains all possible integers. I mean, larger than Piso. So if you take the golden mean, it's a Piso number. So we know several things concerning Piso numbers. So the set of Piso numbers, so that's an amazing result. If it's closed, so it's an infinite set of algebraic integers. It has accumulation points, so it's closed. And the picture is, so the minimum is what we denote by alpha p. So it's the root of p cubed is p plus 1, which is larger than 1. Then you have the golden mean. In between, you have a sequence of Piso numbers which accumulate here. And then you can also accumulate on the right. And the golden mean is the first accumulation points of Piso numbers. So now silent numbers. So alpha is a silent number. If all the Galois conjugates of alpha are in the closed unit list, then some of the conjugate is on the boundary. So you have a point on the boundary and something in the. But you see, if you have something on the boundary, then you also have its conjugate, so you have its inverse. It's stable if you take inverses. So you also have one over alpha. And if you have something something else inside, since it's stable on the take inverses, you go outside. So in fact, inside the unit, this will just like 1 over 1. So alpha is a silent number if it is larger than 1. 1 over alpha is a Galois conjugate, and you have all other conjugates. Okay, and the picture here is not so easy. So the smallest known silent number is the Lemma number. It's here. Here you have a lot of silent numbers. And in fact, silent numbers approximate all Piso numbers. But it's not known, for instance, if there is something in between 0 and the so-called Lemma number. Okay, so now I take, my time is over, but I want to take 2 minutes to state what I proved with Jeremy Blanc. Okay, so this concerns dynamical degrees of birational transformation. So we know from these results and Hodge-Index theorem that dynamical degrees are, if not one, are either Piso or silent numbers. So there are 2 results. The first one somehow justifies the fact that I got interested in these numbers. So the first theorem. So that's this now. So first is a remark. If there exists such a birational morphism, even birational transformation, such that the lift of f to x is regular everywhere, so it's automorphism. So if it is regular everywhere, if you can kill all indeterminacy points after a change of surfaces by a birational transformation, then lambda of f is, so it can be 1, or it can be a quadratic integer, or it can be a silent number. So that's not hard to prove. But the interesting point is that if lambda f is a silent number, then in fact you can construct such a number. So the dynamical degree contains some geometric information. It almost contains a characterization of those transformations that are conjugate after a birational change of transformation to a regular automorphism with no indeterminacy. And if you apply this statement to with previous work by Macmillan and Nagata, what you get is that the infimum of all lambda f for all f in the group of birational transformation of the plane, so the infimum is 1, but if you assume that lambda of f is bigger than 1, then you get the lemma number. The infimum is a minimum and is a lemma number. So if you look at all possible silent numbers, we don't know if there are silent numbers here, but if you look at silent numbers which are realized as dynamical degrees, then the minimum exists. And the last statement, the second statement, so again, it's for the field here. The second statement is on the structure of all possible dynamical degrees. So the set of all possible dynamical degrees is well ordered. So is well ordered and closed. So what does it mean? Well ordered and closed, you know, and well ordered meaning that there is no strictly decreasing sequence, infinite strictly decreasing sequence. Okay, so if you take a subset in this set, then you can find a minimum. Okay. So for instance, here, you know that there is an infinite sequence of Pizot numbers which decreases towards the golden mean. But if you look at dynamical degrees, you know that there is a gap. There is no infinite decreasing sequence. So each time you have a number which is a dynamical degree, then on the right you have a small gap. There is a small interval with no. So it's very similar to the picture obtained by Kerston for volumes of hyperbolic freeforms. That's why I stopped at my slides.
Yes, thank you for the beautiful notes. Let's see if there are any questions.
So if you don't restrict to rational surfaces, is it known that you can realize any Serem number?
No. If you go to, other surfaces are not interested for this question. Okay. If you change the surface, so if you take a surface which is not a rational surface, then the numbers that you get when you do the same construction and compute that these dynamical degrees, you can obtain the number 1, or you can obtain quadratic numbers, or Salem numbers, but Salem numbers which are roots of polynomial with integral coefficients of degree at most 22. So 22 comes from the dimension of the second homology group of K3 surfaces.
Well, I mean, if you go beyond K3 surfaces, then you don't get anything.
No. Okay, so then there are interesting questions. Can you realize the Lehman number as a dynamical degree for an automorphism of a K3 surface? That's true. Correct. But if you consider surfaces which are not rational surfaces and you plot the dynamical degrees that you can obtain, you just get a discrete subset of the real number. Because the degree is bounded by infinity. So I focused on the plane, in fact not because it's simpler, just because it's the most important example.
And are you realizing the golden ratio?
Oh yes, the golden ratio is simple. You take a monomial transformation. Okay, so the monomial transformation such that the largest root of the 2 by matrix is the golden mean, and then you get this number. And I didn't say that, but the dynamical degree for a monomial transformation is just the spectral radius of the matrix.
So that's the way to figure out what happens.
And also, what I didn't say is the link between the two parts. Okay, so if you work over the field of complex numbers, you can look at the dynamics of the birational transformation on P2, and you define entropy as I did, but just for orbits which are not going through indeterminate sequence. And you get the notion of entropy. And then this topological entropy is always bounded from above by the logarithm of the dynamical degree. And under good assumptions, you get an equality. So in fact, this is totally related to the entropy.
Let's stop here, but Nikita will be in charge of the answer.
Okay.